This is video number 95 in our series on tensor calculus. In this video, we're going to analyze a special and very important classification of curves known as geodesics. In the previous video, we demonstrated that when this object, the geodesic curvature tensor, is equal to 0, there's no surface projection for our curve. The only projection is that lies in the direction of the normal. We also said that when this condition exists, the result is a special type of curve that we call a geodesic. Well, what we're going to do now is to analyze geodesics in greater detail. So let's start by reminding ourselves of the definition of our geodesic curvature tensor that we introduced back in video number 93. Well, if our geodesic curvature tensor is going to be equal to 0, then of course this expression has got to be equal to 0 as well. But we know that our normal in alpha is not equal to 0. So if this expression is going to be 0, it's going to be because this factor right here is equal to 0. So what we'll do now is to expand this expression out using our rules for the covariant derivative. Now we've done this before, so I'm not going to do it again. This is the result. What we have is, of course, first of all, a partial derivative of the object, and then we've got two terms, this one that takes care of the upper index, this one that takes care of the lower index. Notice that because this is a surface index, we have to include this factor because we're applying it with respect to a curve index here. So this is the full expression that we're looking for. Well, of course, for the condition we're looking for, this expression has got to be equal to 0. Now, you'll recall that our definition of our shift tensor S alpha phi is simply the partial derivative of S alpha with respect to U phi. So this is our basic definition, and what I want to do is to substitute this basic definition into our expression here. Well, S alpha phi here is already a partial derivative, so this first term is actually a second partial. It is the second partial derivative of S alpha with respect, first of all, to U phi, like this, and secondly, with respect to U psi. All right, and then of course we can use the definition to substitute directly into the rest of the expression. So what we have is a differential equation that is the exact equivalent of this expression right up here. Now, we can simplify this expression even more by making the right kind of choice for the parameter we use for the curve. We're going to say then that u1 is going to be equal to lambda, which in turn is a parameter that has this relationship. It's equal to some constant times the arc length of the curve plus another constant. Now, any parameter that meets this condition, that is linear with respect to our arc length in this fashion, is known as an affine parameter. In video number 88, we derived this relationship. We said that ds is equal to our volume element, square root of u, times du1. Well, of course, we can restructure this relationship to be 1 over our volume element, being equal to the derivative of u1 with respect to s. Well, if we choose lambda as our parameter instead of u1, then the derivative of lambda with respect to s, according to this relationship, is just the constant value of a. Now what this tells us is that our volume element, the square root of u here, is a constant provided we choose an affine parameter for our parameter instead of u1. Well, remember for a curve that our volume element is the determinant of our covariant metric tensor, and for a curve there's only one element, that's u11. So this also tells us that U11 itself is a constant. Well, then in video number 90, we derived this relationship. We said that the Christoffel symbol for the curve is simply 1/2 of this derivative right here. Well, if U11 is a constant value, then this value is going to be equal to 0. So all that means that if we choose to use an affine parameter in place of U1, that this last term right here drops out because the curve Christoffel symbol becomes 0. And this means that our expression simplifies to the following form. This then is the differential form for a geodesic as it is most commonly presented. But always remember that it is only true if lambda itself is an affine parameter. Okay, well let's move on now and explore what is arguably the most significant property of a geodesic. What you see here is known as a functional. A functional is similar to but distinctly different from what we call a function. For a function, we supply values to one or more arguments and apply the appropriate rules and calculations to produce a single numerical result. On the other hand, the argument of a functional is the function itself. The value of I in this expression depends not upon any specific value of arguments, but upon the choice of functions. The result here depends on which function we choose to evaluate. Note that the function here depends upon arguments t, s, and q. T is the parameter that characterizes a curve from values a to b. S is the set of coordinate values along the curve, and q is the set of corresponding first derivatives of s. Note that we treat s and q as independent variables. S does not depend on q, and q does not depend on s. However, both of them are parameterized by t. Now, in the end, we evaluate this definite integral to produce a single numerical value. And the point of analyzing a functional is to determine which of the functions produces minimum or maximum values of I, or what we call extremal values. This is analogous to the idea of finding minimum and maximum values of a function. In that case, we know that extremal values occur at points where the derivative of the function is equal to 0. Well, in the case of a functional, Euler and Lagrange were able to show that extremal values occur only when the function satisfies the Euler-Lagrange equation, which you see here. Functions that satisfy this equation are known as stationary paths and will produce extremal values for I. Unfortunately, we don't have time to derive this equation, so I simply have to present it to you without proof. If you want to dig deeper, you might do an internet search for a branch of mathematics known as the calculus of variations. What we want to do here is to make use of the Euler-Lagrange equation to determine the shortest path or curve between 2 points in a manifold. Now, one comment before we begin. The Euler-Lagrange equation will produce a stationary path. What it won't do is to tell us whether the stationary path produces a minimum value or some other extremal value. We'll need more information to know that. It's analogous to the min-max problems we do with functions. A derivative of 0 indicates either a minimum, maximum, or inflection point. We don't know which it is without performing additional tests. So it is with a functional. The Euler-Lagrange equation is a necessary condition for a minimum length path, but it is not a sufficient condition. More on that in a few minutes. Okay, so let's proceed. Back in video number 62, we derived this expression. We said we can find the length of our curve simply by evaluating this definite integral. Well, you'll notice that the form of this integral is exactly the same as our functional. Now, that would imply that the function we need to be working with, this value of f, is this radical expression right here. In other words, our function f is going to be equal to s alpha beta times these two terms, but remember our definition up here, our q values are the first derivatives like this, so the first term here is just q alpha, and the second one is q beta, and all of this is under the radical, and this then is the function that we need to be working with in the Euler-Lagrange equation. Okay, so we need to apply the Euler-Lagrange equation to this function, and we do it first of all by taking the partial derivative of the function with respect to s omega. Well, first of all, we'd have 1/2 times 1 over this radical times the partial derivative of what's inside it. So the first term is going to look like this. It's going to be 1 over 2f, f is just this radical expression, times the partial derivative with respect to s omega of what's inside the radical here, s alpha beta q alpha q beta. So this would be the partial derivative of f with respect to s omega. So likewise, for the second term, we'll have, first of all, a derivative with respect to t of this partial, and again, we'll have 1 over 2f, same idea, 1/2 of, times 1 over this radical, times the partial derivative of what's inside the radical. So what's left here is the partial with respect to q omega of this same expression, s alpha beta q alpha q beta, like this, and this whole thing has got to be equal to 0. So this then is the expression that has to be satisfied in order to find the stationary path. Going back again to video number 62, we have our metric equation that looks like this. Well, we can divide both sides by dt squared, and we can express it in parameter form where t is the parameter. Now, in this form, it's very obvious that the right-hand side of this equation is equal to the function squared. This is f squared, as we've defined it up here. Well, this in turn can be reorganized. We can take the square root of both sides and reorganize it this way. 1 over f is equal to dt ds. Okay, now here we can play the same game we played a few minutes ago. We'll choose an affine parameter for our parameter of our curve instead of t. We're going to use lambda instead of t. This is our affine parameter. And remember what that means. Lambda is equal to a constant times the arc length plus another constant. And this derivative then just equals the value of a. Now that in turn tells us that our function f is a constant as long as we're using an affine parameter. So what we're saying is this: if we don't use t but we use lambda as an affine parameter, then this factor of f is a constant. Where lambda is concerned, that means it can come out of the differentiation as a constant, and because it exists in both terms, we can divide it out throughout the expression, and therefore we completely eliminate this factor of 1 over 2f. And that leaves us with this form. This form is much simpler and makes our life a lot easier. Of course, it's only true if we're using a parameter of lambda, but that's a restriction we can easily live with. All right, we've got an expression with two terms, so we'll expand them out one at a time. We'll start with this guy. Remember that s and q are independent variables, so where this partial derivative is concerned, the q factors are constants. We only need to take the partial derivative of the first factor. And that's all there is to that one. Next, we'll expand out this term right here. This time, because s and q are independent variables, the partial derivative only affects the q factors. S alpha beta is a constant where q omega is concerned. So we can expand this one out simply using the product rule. Now take a look at this particular factor. Q is an independent variable, so anytime alpha and omega are the same value, this partial derivative is going to be equal to 1. But anytime alpha and omega are different, the partial is going to be equal to 0. Well, that's nothing but our delta factor. So this is the equivalent of delta alpha omega. And of course, that will absorb the alpha index here, leaving us with omega. Likewise, this factor is delta beta omega, and it will absorb the beta index here, leaving us with omega in this position. All right, well now we've got to find the derivative of that expression with respect to lambda, so we have to find the derivative of this expression. This time, both s and q are dependent upon lambda, so we have to use the product rule twice, once on this term and once on this term. But as I take the derivative of this first factor, I want to use the chain rule to express it because I want to have a factor of the partial of s omega beta with respect to s alpha. So it's going to look like this. We're going to have the partial derivative of s omega beta with respect to s alpha times ds alpha d lambda. So don't let me lose you here that what we're doing is saying that the combination of these two factors together is the chain rule applied to the derivative of this one factor. So of course we have the last factor q left over here that we have to include. So this is q beta. And then we're going to complete the product rule here. So we've got s omega beta times the derivative of q beta with respect to lambda. And of course I can deal with the second term here in exactly the same way. All right, let me clean this up a little bit. First of all, notice that this factor right here, according to our definition, is nothing but q alpha. So we can write the first term this way. Likewise, this factor over here is really q beta. So we can write the third term this way. Now, notice that if we flip these two indexes and rename alpha to beta, both positions, this term is exactly the same as the second one. So we can combine the second and fourth terms together into a single term. Now that we've expanded out this term, this one, we've got to combine them together, which means we have to take this term and subtract all this stuff, and then set the result equal to 0. Next, I'm going to multiply through by negative 1/2, and then I'll do some reordering and grouping of the terms. So multiplying by negative 1/2 changes the sign of every term, adds a factor of 1/2 to these first three, and of course kills this factor. I've moved this term all the way out to the front here, and then this term's right here, this term's right here, this term is right here. Notice I've swapped the indexes alpha and beta, which of course I can do, and then I've factored out the factor of 1/2 that's created for each of these, and I've factored out the common terms of Q alpha and beta in the opposite order here. So quite a bit of reorganizing, but that's the end result. Okay, now surely you recognize this factor right here as the Christoffel symbol of the first kind. This is just gamma, omega, beta, alpha. So we'll make that substitution, and at the same time we'll also multiply through by the contravariant metric tensor. So I replace this expression with the Christoffel symbol of the first kind here, and also multiply through by this factor. All right, well, these two factors together will produce a delta sigma beta, and that in turn will absorb the beta index, leaving us with sigma in this position. And over here, this combination will raise the first index into this position, giving us sigma. And finally, I'm going to replace the Q factors throughout with their basic definitions. Remember, Q sigma here is really the derivative of S sigma with respect to lambda. So in this case, what we're going to have is a second order derivative. At the same time, I'm also going to rename sigma to alpha and alpha to omega. So this first term will be the second derivative of S alpha with respect to lambda. And then we're renaming sigma to alpha, alpha to omega. So this is gamma, alpha, beta, omega. Q beta is just the derivative of S beta with respect to lambda. And Q alpha here, which we're renaming, will be ds omega with respect to d lambda, all set equal to 0. Okay, well, all of that was pretty tedious. You'll probably have to go over it a couple of times again to make sure you understand all the steps. But surely you recognize the result here is the same equation that we derived a few minutes ago for a geodesic. Since we derived it this time from the Euler-Lagrange equation, we now know that stationary paths are the equivalent of geodesic curves. However, remember that stationary paths may or may not be minimums. They could represent other extremal values. Based on the nature of a manifold, it may be possible to connect 2 points with more than one geodesic curve. If that's the case, then only one of them can be the shortest path. So what we can say is this. The shortest path between 2 points will always be a geodesic. It is a necessary condition. However, not every geodesic is necessarily the shortest path. Let me illustrate what I'm talking about using a spherical surface. Here we have a spherical surface with 2 points here and here, and I have connected the 2 points with a geodesic curve. Now for a spherical surface, that's just a segment of a great circle. And as it turns out, this is the minimum length path between these 2 points. However, it's possible to connect these 2 points with a geodesic in another way. We can connect them with a geodesic that goes all the way around the backside like this from one point to the other. We can connect them this way or this way. Obviously, this one is shorter than this one, therefore this is the minimum path. Okay, in a lot of literature, you'll see a geodesic defined as the shortest path between 2 points. But that's really not a good definition because, obviously, from this illustration, it's not always true. So it's better to define a geodesic as we have, that being that it is a path that has only a normal curvature component. It has no surface curvature component. And one of its properties is that a geodesic is also a stationary path and therefore may or may not represent the shortest path between 2 points. What we need to do is to find all the ways in which we can connect 2 points with geodesics, and obviously the shortest one of those will be the shortest path between the 2 points. Okay, with that, let's take a break and do a quick review. In a previous video, we defined a geodesic curve as one in which the geodesic curvature tensor is equal to 0 at all points along the curve. This means that it has no surface projection but only a normal projection. Well, in this video, we demonstrated that this differential equation is the equivalent condition to this. It's the same condition, just expressed in the form of a differential equation. We then showed that if we make a particular choice for our coordinate value for the curve, being that of an affine parameter, we can express the same condition this way. So this is the differential equation form for a geodesic curve, provided we're using an affine parameter. And remember what that means, that our affine parameter will be equal to a constant times the arc length plus a constant. So as long as this condition is met, we can express the condition for a geodesic curve in this form. And finally, using the Euler-Lagrange equation, we were able to show that a geodesic curve is the equivalent of what we call a stationary path. And that means that it is a necessary condition for being the shortest possible path between 2 points. But remember that we also demonstrated that it is not a sufficient condition. So what we can say is this: the shortest path between any 2 points in the manifold will always be a geodesic. However, the converse is not necessarily true. There may be multiple ways to connect 2 points in a manifold with geodesics, and only one of them can be the shortest path. Well, in the next video, we're going to introduce the concept of the parallel transport.